They're doing 6.5b today. And the first question is dy dx equals 1/3 times y times 4 minus y. And the question says make a slope field. So of course the slope field is when you plug a bunch of points into the slope and do all those tick marks, right? So I'm going to just do some positive numbers. So first of all, I'm going to have y equal 4. So if you stick 4 into this, it's 1/3 times 4, which is 4/3. And then 4 minus 4 is 0. So it's 4/3 times 0, which comes out to 0. So that means when the y value is 4, the slope is 0. So for example, at the point 1, 4, slope is 0. Or at the point 2, 4, slope is 0. Slope is 0 all the way across here whenever y is 4. Okay, then also, if the y is 0, this would be 1/3 times 0 times 4, which comes out to 0. So down here, when the y is 0, the slope is 0. Okay, let's plug in 2 now for y. 4 minus 2 is 2. 1/3 times 2 is 2/3. 2/3 times 2 is 4/3. So it's going to be fairly steep, not super steep, but more steep than 1, so like right around here. So there's the slope of 4/3 all the way across there. Now I'm going to plug in 3. 4 minus 3 is 1. 1/3 times 3 is 1. 1 times 1 is 1. So that means at 3 the slope is 1. So that's a little bit flatter than those other ones. Those were 4/3. And just to save us some brain power here, 1, just take my word for it, it also spits out 1. So the slope is 1 here. So that's the slope field. So right now we're done with this problem, where it says make the slope field. But sometimes it says connect to the slope field as well. So I'm going to go ahead and do that, even though the directions don't tell me to. So it would be flat at the start, but then it would go up like this and then steeper, but then it would get less steep and flatten out. So see that curve that goes like this and then like this and then like that? So that curve is the main topic today. This kind of a shape. This is called the logistic curve. We've had a different curve this chapter before this. Remember, the slope has been proportional to the y value often. That's what I ended up with yesterday. And I said, okay, we've done this a lot, so we know now that this is going to lead to this y. So this derivative, this differential equation, if we do the antiderivative of it, it leads to here. And the curve that goes with this is the exponential curve. It keeps getting steeper and steeper and steeper, right? Steeper and steeper and steeper. Gets really steep. So this derivative kind of looks like this, right? See how it has the ky, but then it has this extra 4 minus y. So this is the old kind of a curve, but the new kind of a curve is when the derivative is ky times m minus y. So k is a number, and then m is a number. And it's possible to do the antiderivative of this. But that's beyond what we're going to do in this class. I do expect that you know how to do the antiderivative of this. This antiderivative is harder, so we're not going to do that. I'm just going to tell you what it would end up being if we did the antiderivative. If you do the antiderivative of this, you get this kind of a curve. But if you do the antiderivative of this is what you end up with. You end up with y equals m over, and then in the denominator it's 1 plus e to the c times e to the negative mkt. This power here is negative mkt. So I'm just asking you to take my word on it, that if we did the antiderivative of this, we would end up with that. And the purpose of this problem was to show you what the curve would end up looking like. So the curve that goes with this is the logistic curve. So notice that when things start out, the logistic curve looks identical to the exponential curve. See how that part of the graph is the same as that part of the graph? So for the first few t's, or for the first few whiles, you can't be sure which kind of a curve you're dealing with. If you just had this part of it, you wouldn't know if it was going to keep going up and up and up, or if it was going to turn around. All right, next is a vocabulary term. This is the carrying capacity. And I'm going to give you a biology definition for this and also a math definition for this. The biology definition is the population that an ecosystem can sustain. carrying capacity is the population that an ecosystem can sustain. So, for example, let's say you've got a pretty decent sized forest. So there's some wolves in the forest. But there's only a certain amount of water and shelter and food in that ecosystem. So the wolf population is never going to get super huge. There's only a certain number of wolves that forest can sustain, and that number is called the carrying capacity. Now, it turns out that as time goes on, the wolf population is going to get closer and closer to that number. So the mathematical definition is, as time goes by, the population will get closer and closer to this number. As time goes by, the population will get closer and closer to this. And the words closer and closer, that sounds like a limit, right? So that's why this is the mathematical definition of it. But that's actually what happens. If the wolf population gets really big, then some of the wolves will not survive, and then it'll get closer and closer to the carrying capacity. Or if there's not very many wolves in the forest, and there's tons of extra food, then the wolves will thrive and get closer and closer to that limit, to whatever, maybe it's 1,000 wolves or something that a certain forest can deal with. Okay, so now we'll look at this question. For this question, dp dt equals 0.0008 p times 700 minus p. And p is the number of squirrels, and t is the time in months. And for part A, we're going to find the formula for P. So this derivative, is it looking like this? Yes. Okay, so that means we have a logistic curve. So that means we know that the y is going to look like this. In other words, in this case, the p. So we can write p equals, it's going to be a fraction. What's the number for m? 700, right? So apparently that goes on top based on this template. So 700, and then 1 plus e to the c, that stays there, and then times e to the negative. All right, so we already decided m was 700. What's k? 0.0008, right? So to figure out the exponent, I have to take the m and multiply it by the k. So we would take 700 times 0.0008. So I did that earlier, and it comes out to negative 0.56. So just keep in mind, I got this by taking m times k. So all I've got left is the c. What information would I need if I was going to figure out what c was? I would need a point, right? Or yeah, the starting population would be the best one because it would be nice if it was a 0. Okay, so that information is included in the problem. I just didn't write it down at first. So at time 0, there's 20 squirrels. So now I'm going to use that information to find C. So I put 20 in for P. And 0 in for T. So I just put a 0 there for T and a 20 there for P. Of course, negative 0.56 times 0 is 0. And then e to the 0 is 1. So this is just e to the c times 1, which would just be e to the c. So what I've got now is 20 equals 700 over 1 plus e to the c. Now I'm going to multiply this to the other side. So it'll say 20 times 1 plus e to the c equals 700. Then I'm going to divide the 20. So 1 plus e to the c is 35. 700 divided by 20 is 35. And then finally subtract the 1. So e to the c is 34. Okay, so now I can rewrite this and put 34 where the e to the c is. So I've got p equals 700 So then that's the final answer for the population equation. You okay, Lucas? Seems like you have a question.
Yeah, I'm fine.
Okay. Oh, this would be part B, sorry. That was part A. Part B is find the carrying capacity. So the carrying capacity is what the population is going to get to be eventually. So it's the population, but it's what happens as time goes by. So time is going by means time going to infinity. And it's what the population gets closer and closer to. So it's a limit. So we got to take the limit as t goes to infinity of this formula that we just got, the 700 over 1 plus 34 e to the negative 0.562. So this is back to limit laws. We're going to take the limit of the top and the bottom separately. So what I'm saying is limit goes past divide. Does limit go past plus? Yeah, so I'll put the limit in front of the 1. And then the limit in front of the 34. What about this times sign here? Limit will go past that as well, right? And then let me rewrite this. It's e to the negative power. So couldn't I put that downstairs, and then that would make it positive? So that's 1 over e to the 0.56t. So this step to this step was a bunch of limit laws. Limit past divide, limit past plus, limit past multiplication. And then rewriting this. So what's the limit of 700? 700, right? Then the limit of 1 is 1. The limit of 34 is 34. Okay, so here, if t gets really big, I'm going to be taking 2.7 to a really big power. That's going to get really big. But then it's 1 divided by that really big number. So that's getting close to 0. So this is 700 divided by 1, which is 700. So that means that as time goes by, there's going to be more, the squirrel population is going to increase, but it's going to increase and get closer and closer to 700. And that also means that there's only enough food and water and shelter in this forest where 700 squirrels can be get enough food, get enough shelter. It's the amount that the forest can sustain. So that's called the carrying capacity. So now we're going to find the number of squirrels after 10 months. So which formula should I use for this? The one that's P, right? That's population. So that's 700 divided by 1 plus 34 e to the negative 0.56 times 10. It's P of 10. So I did that earlier. And it comes out to 558. So there were 20 squirrels to start with. But then 10 months later, there were 558. Squirrels are pretty quick to take over a neighborhood. I'm sure you've noticed that in your neighborhood. Maybe. If there's any trees in your neighborhood, you have squirrels. Okay. Now D is how fast is the population growing when t equals 10. So how do we figure that out? How fast the population is growing. That's the derivative, right? So that's, this question is so much fun, we're going to do it two different ways. So here's method one. This is how fast it's growing is the derivative of the population. Sorry, the variable's t. So we could do quotient rule on this, right? Or we could do math 8. If we did the derivative by hand, we'd have to use quotient rule. So I did math 8 earlier, and I got 63.488. And that would be squirrels per month, right? Because it's a rate. Okay, but actually it was kind of silly for us to use the calculator to find the derivative. Because this right here is the derivative equation, right? So to find the derivative, we could have just used this. Now, this is a little bit of a strange equation because it just has p in it. It doesn't have t in it. But we can still use it. All right, so we're going to do dp dt at 10. But what is the p at 10? 558. That's why we figured out part C here. So it's the point 10, 558 that we're plugging into the derivative. So that would be 0.0008 times 558 times 700 minus 558. So that's the other way to get the 63.488. So I want you to realize that this actually is the derivative that was given to start with. What is the size of the population when it is growing the fastest? What is the size of the population when it is growing the fastest? So this is a maximum question, right? The biggest. Is it asking for the maximum population? No, it's not saying when is there the most squirrels, right? It's saying when is it growing the fastest. So it's asking for the biggest growth rate. It's asking for the maximum rate. Okay, so before we answer that question, let's take a step back. If the question was asking for the maximum profit, what would you do? You'd take the derivative of profit, right? Because here's a graph of profit, and often the max happens when the slope is 0, right? So the whole process of taking the derivative, setting it equal to 0, and undefined, that's how you find the maximum. So if you want the maximum profit, you take the derivative of profit, p prime, and set it equal to 0 and undefined. Okay, so if you want the maximum rate, you're going to have to take the derivative of the rate and set it equal to 0 and undefined, right? So here's the rate. So we're going to have to take the derivative of this to get the maximum of this. Before we take the derivative of that, let's rewrite it. I'm just going to distribute. So we already know 0.0008 times 700 comes out to 0.56. So that's 0.56p minus 0.0008p squared. So there's the rate function. So now I want the maximum of this. So I need to take the derivative of this. So dp dt's derivative is 0.56 minus 2 times that, .0016, so there's the derivative of the rate. Now I'm going to set that equal to 0 and undefined. It's never undefined. I'll just set it equal to 0. Subtracting that over. And 0.56 divided by 0.0016 is 350. So now we need to confirm that this is a max, right? So often how we do that is we do a number line. But that's going to be kind of awkward on this problem because we don't have t values. We just have p values. So I want to remind you that another way to test to see if it's a max is to look at the concavity. If it's concave down, then it's a max. So now I'm going to take the second derivative of the rate. And that's just negative 0.0016. So that means that the rate graph, the second derivative of the rate is negative. So that means that the graph of the rate, here's the rate. The graph of the rate is concave down, which means that this critical value is a max. Since dp dt equals 0 and, dp dt prime equals 0 and dp dt double prime is less than 0, is negative, there is a max at p equals 350. So that means that when the population is 350, when there are 350 squirrels, the population is growing the fastest. Everybody doing okay? No questions about anything? So the deal was that sometime data starts out looking like this. And when it looks like that, sometimes it's going to keep growing and growing and growing and get out of control. And other times it's going to grow but then flatten out. So if it's going to get out of control, then it's exponential, which means the derivative is this, right? If it's an exponential graph, this is the derivative. But if it's not going to get out of control, if it's going to be logistic, then the derivative looks like this. So the new topic today is if you tack on this extra thing on the end of the derivative, it pulls back and makes it look logistic instead of exponential. So that's the idea, the logistic curve today. All right, thanks for listening.